Hello everyone and welcome. To start things off, let's look at the major moving on. The core goal of our project is we have established five primary objectives of this experiment. First, data collection. Our baseline step is to collect raw data angular velocity. Data we achieve by utilizing the internet gyroscope sensor of the two separate smartphones. Tracking using the app Firefox app alongside an external MPU sensor hardware module. Second, the device composition. With three different hardware setups running simultaneously, our next objective is to directly compare this gyroscope measurement to analyze how baseline drift and noise variance differ across distinct sensing device. Thus, initial data reliability. Before jumping straight into complex filtering, we want to see how much we can improve the signal stability through simple hardware redundancy, especially by averaging the raw data sensor output for multiple devices. Fourth, advanced noise reduction. This is where the core engineering comes in. We apply the Kalman filtering algorithm to aggressively minimize the high frequency noises and drastically enhance the structural accuracy of the measurement data. Finally, performance analysis. Our main objective is to critically analyze the overall efficiency of combining the sensor fusion and filtering techniques. We want to qualify exact how much closer we come to achieving the perfectly stable, reliable and angular velocity signal. With this objective setting our roadmap, let's
Okay, I'm going to explain our experiment procedure and also the way we how we conduct the experiment at oral. So first and foremost, we was mounted the two smartphone running with the Firefox apps and also an ESP32 with an MPU 9250 gyroscope sensor in the same orientations. So the experiment we set up all these three devices to simulate the rotational motion of a satellite lah. Then next we collected the gyroscope z-axis data from all three devices, then recorded the recorded data from each devices we exported into the CSV files and analyzed using Python. So then we compare raw measurement from the two smartphones and also the MPU sensors. Since each sensors contains a different noise and also some measurements errors, so that's why we applied sensor fusion by averaging the overall data from all these three sensors. So after that, a Kalman filter was applied to the average signal to reduce the noise and produce a smooth and more accurate angular velocity measurement lah. And then finally we analyze and compare the raw data and also average data and Kalman filter data. Then the result show the sensor fusions and Kalman filtering improve the stability and reliability of the gyroscope measurements, which is important for our satellite attitudes control systems. So here you can see our experiment setup for our satellite attitude simulations. Here we use two smartphones with the Firefox applications and with ESP32 boards equipped with MPU gyroscope sensor. So all these three devices we fix in the same orientation to measure the same rotational motion to get accurate data. So during this experiment, we rotate the setup like a small satellite motion system while recording the gyroscope data from all the devices at the same time. And then the signals were sent to the laptop where we plot and compare the results. So from these setups, we can later apply for a data processing method like averaging and so Kalman filtering and to improve the accuracy of the data and then the gyroscope readings. So this will help us to simulate how real satellites attitude control systems is reduce noise and also improve the stability using the sensor fusion techniques.
Uh, so I will explain the Kalman filter and its application in aerospace system. So basically, the Kalman filter is an estimation method used to determine the true state of a system when the measurements are noisy or inaccurate. In aerospace applications, sensors like GPS, IMU, and barometers often have errors, so we cannot rely on raw data directly. So instead, the Kalman filter combines two things: a mathematical model of the system and sensor measurements to produce a more and better accurate and reliable estimate of variable like positions, velocity, or altitude. Uh, so, working principle of Kalman filter. The Kalman filter works in two repeating steps. First one will be the predictions, and the second one will be the updates. So in the prediction step, the system use a mathematical model to estimate the next state of the system. So this is based on the previous value and system dynamics. Then in the update step, the filter takes the actual sensor measurements and compares it with the predicted value. If there is a difference, it will adjust an estimate to reduce the error. So the key idea is that the filter decides how much to trust the prediction and how much to trust the measurements depending on their uncertainty. This balance is what makes the Kalman filter very powerful in real life system. So as for mathematical model, the system is represented using a state space model. So the process equation is the first one there. So the equation represents how the system changes over time, including process noise. And the second equation is the measurement equation, which will shows how the sensor observe the system, including measurement noise. So these two equations will form the basics of the Kalman filter model. These are the main Kalman filter equations. First, we predict the next state and its uncertainty using the system model. Then we will calculate the Kalman gain, which will decide how much weight to give to the prediction and the measurements. After that, we update the state estimate and reduce the error. So this process will keep on repeat continuously to improve accuracy over time.
Okay, as for the result and discussion part, after compiling the data from all devices and sensors in CSV form, we proceeded to generate a graph using Python, where the common filtered was implemented, and also the difference between data that has been common filtered and non-filtered raw data were compared. As you can see here from the graph next to me, the green line, the thick green line shows the compiled command filtered line from every devices and sensors that we use, and the protruding fine lines that you see, although it's a bit hard to see if you look carefully, there are a few lines protruding from the graph. Those are the raw data from each of the respected devices, where you can see there's a lot of noises, that's why it's protruding a lot. Notice that the green line is more smoother and seems more retained towards the origin. This is because the filter has eliminated much of the useless noise from the raw data, and the green line shown here is a much more accurate and smoother line, basically the readings that we want, and a more accurate reading that goes with the movement of the device and the sensors that we did for this experiment. Moreover, this common line is also compared with the raw average line, showing that there's very low protrusion compared to the raw average line if you look carefully, which shows that this common filtered method is much more gives a much more accurate reading than compared to this finding just taking out values from every devices and finding the average from it. So, hence, in conclusion, we can say that the gyroscopic data were successfully collected from two smartphones and also an MPU sensor. Averaging multiple sensors output improved the measurement consistency from what we have seen, and also the common filtering greatly reduced noise and sensor drift, which is also why we could get a much more accurate reading at the end. The process data provided a more accurate and stable estimate of the angular velocity, as mentioned just now. And at last, the experiment demonstrated principles used in satellite altitude demonstration and control system.